So here's how digital is going to work. Official computer science terminology. All right, so I've got this signal. And to make it digital, what I want to do is I want to take the signal in. Like let's say I'm going to have the digital equivalent of a microphone. I'm going to take in sound signal. And what I want to do is reduce it basically to a series of numbers. So then it looks like the RGB data that we've played with. So then once I've got those numbers, I could put them in a file or send them on a network or whatever. So that process is called digitization. Taking in analog, reducing it to numbers. And I'm going to show you how that works. So the way digitization is done is I've got this signal I've drawn sort of big. And I want you to imagine, so the signal is analog. Let's say this is really in the air, and that is really perfectly what the signal looks like. And so I want to try and capture that signal. So the way this is done with digitization is called sampling. And what I'm going to do is I'm going to run a little system which is going to measure what the height of the curve is very quickly over time. And so I'm going to use as my example the audio CD format. So the audio CD format digitizes sound, and it samples 44,000 times per second. So I've drawn the sample sort of coarsely on the curve here, but in reality, for sounds that you can actually hear, the samples will be very tightly spaced against the curve. So it's going to look pretty good. All right, so here's what sampling does. Let's say this is going to be my first sample here. The way it's going to work is I'm going to have a notional kind of 0 line going down the middle here. All right, so that's going to be sort of the baseline. And the way these sounds work is I've always talked about them going above the 0 line, but actually half the time they're below. So we'll record it as a series of both positive and negative numbers. So the way the sample is going to work, let's say I start recording right here. This is going to be my first sample. So what I'm going to do is I'm going to look at like, well, how high is this above the 0 line? And I'm going to measure it. And I'm just going to have some scale where, let's say, way up here for a really loud noise will be, the way audio CDs work will be about 32,000 would be the max. And so in that scale, maybe this is kind of not a very loud sound. So I'm just going to measure on that scale. Well, just where is that number? So let's say that one turns out to be 1,003. So I'm going to record that number. OK, 1,003, that's my first sample. So then 1/44,000th of a second later, the curve, and now this is this example, the curve is moving much farther than it would for real sound here, just to show. So let's say for this next sample, I gauge the height of that. I'm like, that's about 1720. So I'm going to record that number. That's going to be my second sample. Now here's my third sample. 1939, and my next sample, 2102, and so on. So I just keep sampling this thing over time. Now here's going to be a bunch of positive numbers. Eventually down here it's going to be a bunch of negative numbers. That's fine. The result is I take signal in and I just reduce it to this like big stream of numbers. So this is not a perfect process, but it does work very well. There's two sources of problems. One source is, let's say that I was gauging this very first sample, and I said, well, let's call that 1,003. What if really that signal, it was like a little bit higher than 1,003, but it wasn't quite so high as 1,004. But in my system, I'm stuck picking one of those two numbers. It's either 1,003 or 1,004 in my system. And so there's maybe a little tiny error there as I kind of put it in the nearest bucket. And audio CDs, it's a little bit of a detail, but I'll mention. So they use numbers between roughly between minus 32,000 and plus 32,000. And the reason is that's the range of numbers you can store in 2 bytes. So the byte and its 8 bits comes back here. And so it turns out on an audio CD, one sample is stored in 2 bytes. And so that kind of gives us how many different buckets, how many distinct numbers we can have. All right, so that's a small source of error. And I should just mention, so audio CDs, I think by most accounts, sound fantastic. Like, whatever the quote-unquote error I'm mentioning here is like, well, it's pretty small. The other source of error, which also for audio CDs is not a problem, is like, well, what if the signal had some big excursion, like it went way up and then it came down before my next sample came in? I could miss something. And it turns out for audio CDs, just for the range of sound, a sound that did out in an audio CD would be outside of human hearing. So for the most part, that's not really a problem. All right, so those are the two sources of technical imperfection. But in reality, this works really well for audio CDs. All right, so what I've done is I've taken in the signal, and now what I have is just like, there's a lot of numbers. And so you can put those in a file or store them on a CD or whatever. So I think this leads to the natural question of like, OK, well, how does playback work? Right? Well, I don't just want to look at these numbers and be like, yeah. No, of course, you want to take them in with your ears. All right, so here's how it's going to work. It's going to be sort of the reverse process. So this is called digital to audio conversion. And there's a piece of hardware, a chip that's specialized to just do this. What the digital audio conversion is going to do is it's going to take in the numbers. And I swear, the phrase that comes to mind to this is connect the dots. So what this thing wants to do is to make actually a pattern of electricity that exactly follows the original signal. And then that electricity, then we can feed into a speaker, and the speaker will make it back into sound. So what the digital audio converter is going to do is it's going to look at this first number, 1003. And it's sort of like it puts a dot like that far above the line. Like, OK, 1003, got it. And then it looks at the next sample, 1720. All right, so it's going to put a dot that height. And then it's going to basically draw a line. It's like, OK, I'll connect those first two. And then it takes the next sample, and the next one, and the next one. And you can see you sort of get these dots. And I drew actually straight lines between those samples. As you can see, even though the original was in some sense curved, the straight lines put together, it does basically capture the shape of the sound. And as I was saying, for audio CDs, because really the samples are so close together, the straight lines work very, very well. So I've drawn sort of in gray. So the effect of going through these numbers is it's able to recreate the original signal. So this goes the other direction. Take in a bunch of numbers, recreate the signal beautifully, and then we can put that in the speaker, and now you're hearing whatever the original recorded sound was. So that's how it works. Also, I just sort of mentioned as the chip that does that, the D to A converter, I see that sometimes in marketing materials for like stereos or MP3 players. It's extra awesome D to A converter. So you may actually, just as proof that I'm not making this up, you may see that like a box or something that you're buying. All right, so those are the two directions. That's sampling to record it and D to A conversion to play it back. So I think the natural question here would be, why? Why go to all this trouble? Like, it wasn't my little telephone diagram. It was actually simpler, right? I just had the microphone. I hooked up to the wire, hooked up to the speaker. So what is the advantage of putting stuff, and then we would say technically taking the data and putting it in the digital domain? It used to be, it was in the sound domain, and then it was in the electricity domain, but now I put it in the digital domain of just numbers. And we're going to see there's actually a lot of advantages to having the data just be in the digital domain. So I'll talk about those. All right, so the first thing I want to think about is errors. There's going to be one big advantage for digital. And so when I described that I'd recorded this thing as numbers, 1003, 1720, or whatever, I'll take as covered earlier. So really, when I say numbers, that means in the computer, it could be just zeros and ones. There's just so 1720, there is just a pattern of zeros and ones that represents that. It does take 2 bytes to do it, but that does work. So an audio CD, at the end of the day, what's recorded on an audio CD is really the pattern of zeros and ones that makes up the series of numbers that then, when fed into the DDA converter, makes the music. So if you got a microscope, and actually on the CD, it really is little peaks and valleys. Like there's a physicality of the ones and the zeros you can actually see. Well, OK, with a microscope you can see. All right, so I want to think about, let's think about audio CD playback. So the way it works is there's a laser that's aimed at the CD, and it's trying to kind of pull off the patterns of ones and zeros so that it can remake the sample numbers so that you can make the music. So what is that going to look like? And we talked about this a little bit before in my networking section. I'm going to say, well, it's going to look kind of like this. The pattern, the laser is looking at the CD, and let's say the first number it sees is a 1. Well, I'll say that that's a 1. And then the next thing it sees is a 0, and then there's a couple ones, and then a 0. So it's reading the ones and zeros off the CD. That's what it looks like in the abstract. Is that really what it's going to look like? coming off the CD, if I hooked an oscilloscope up to the laser and looked at the electricity coming out, is it going to look like that with perfect 90-degree corners, right? No. There's going to be noise, right? All the little wires and magnets and layers and the CD like probably jiggling a little bit while it's signaling. Here's what it's going to look like. It's going to look like that. You've got the ones and the zeros in there, just as we had for the analog scheme. There's noise crudding up on top of our signal. That's what we actually get. We get back signal with noise. All right, now this is a little bit of a punchline moment here. Suppose you're the CD player, and you're like, oh no, my signal up the CD. It's got all this noise. But look, do you have any problem picking the ones and zeros out of there? No. Right? You can have a lot of noise on that signal, but the ones and the zeros, you still pick them out. Right? And so the effect of the noise on the digital signal, it's nothing. Right? I can see 1, 0, 1, 1. So that means I could have the CD, all sorts of cruddy noise on it, and I play it back. It doesn't come back like pretty close. The playback, it's perfect. Right? It's just like the signal came out ideally. So that's why, or this is one reason, that's why digital sounds better. Right? I mean, I had to kind of string together all these steps. But I can take the signal I care about, encode it as zeros and ones, so basically it's come through the square wave, and it gives me a lot of noise resistance. It's not perfect. All right, if you drill a hole in the CD, there could be a mess up big enough on the CD to really mess things up. But it can stand a lot. In particular, it's much better than analog. Right? With analog, that hiss was just mixed right in with the sound that I wanted to hear. So this is the big jump up in, lots of things digital. So whatever. Now you know. That's how that works. All right. So noise reduction, or noise elimination, really is one big example. I'll just mention for completeness. So the way CDs work is that obviously for the zeros and ones, it is greatly resistant to little specks of dust or whatever that cause noise. It is also the case that the CD actually stores in a sense, multiple copies of the music. It's a little bit like packets on the network. Remember we talked about packets and resend? The CD actually has multiple copies, and the copies are marked with checksums, which I talked about in the networking section. And so the CD can actually notice if there's like a little teeny hole or something where one part of the music didn't come out right, it can go to I'm oversimplifying a little bit here, but basically it can go to a fallback copy. And so it can swap that one in and just keep playing. And so that is a higher level of error resistance. It's called error detection and correction that CDs have. And actually DVDs do as well. So that's how I guess you want, with someone else's DVDs, you could figure out like, well, how big of a hole can you drill in a DVD and still have it play? I don't think it's very big, but it can stand a little bit of just missing data, and it has another copy that it can. So also that works because it's digital. That we can have this logic and these if statements to kind of checksum one copy and have an if statement that says, oh, I'm going to go get the other copy in some cases. So yeah, analog, that wouldn't work. All right, so let me show you another thing that you can do with digital. All right, so suppose the numbers that I had coming off of my audio CD were these. So 12,000, 12,002, 12,006, 12,007. This is actually pretty realistic. That the sampling is so fast on the audio CD that the signal appears to just change very slowly for sounds that actually that you can hear. All right, so what do you notice about those numbers is that, well, they're pretty near to each other, right? Like even though the base number 12,000 is big, the change from one sample to the next, it's not very big, right? It's under 10. In fact, it's just it's under 5. So I'm going to propose a scheme, a compression scheme that we could use so that we could record the audio data and have it take fewer bytes, have it take up less space. So here's the scheme I'm going to propose. What if at the start of the audio data I just put whatever the first number is. So I record that first sample. And then after that, I don't record any more samples. What I do is I just record the difference of each sample to the next. So in this case, I would end up with 12,000, and then I would say plus 2, because the next sample was 12,002. And then I would say plus 4, because the difference between the third sample and the second was going up by 4. And so I end up plus 1, plus 3, minus 5, plus 1. I just end up with these little numbers. So now you just have to convince yourself playback can still work. So long as playback knows about my scheme. Right? Because playback has to know the sample number. So playback would say, all right, this is Nick's crazy, you would call this a delta scheme, because you're just recording the deltas. So playback could know, all right, 12,000 is the first sample, and it would just have to do the arithmetic to recreate the sample. So it could just work, it could just undo it to work out that the samples were 12,002, 12,006, 12,007, and then using those samples, feed those into the D to A converter to really recreate the sample. OK, so what's the advantage of this? What's better about plus 2, plus 4, plus 1, plus 3 than 12,002, 12,006, 12,007? I mean, it sort of gets back to bytes. What this comes down to is those numbers are smaller, a lot smaller. And the reality is I could record them using fewer bytes. Right? If you just think about the amount of space on the CD, the amount of little pits and valleys or whatever, if I use this scheme, and I'm glossing over a little bit of complexity, but basically I could take that sound and I could record it maybe using just half as much space. Because I'm just being cagey about making the numbers small in most cases so that maybe I could just use 1 byte, whereas maybe previously I had to use 2 bytes for each sample. And I've added some complexity. So that is compression. Right? We've talked, and all media, sound and images, all these sort of things, they're typically stored in some compressed format. And this is an example where instead of just storing the numbers in the total straight ahead obvious way, we're going to have some scheme that takes advantage of the fact, and this is true for images as well, that the numbers don't tend to just jump around randomly. That if I look at one pixel in an image, and it's got certain red, green, blue values, and then suppose you look at the pixel right next to it, right, super, super close. Probably the red, green, blue values of that second pixel, they're probably really similar, really close to the red, green, blue values of the first pixel. And so maybe you could take advantage of that, have some delta encoding scheme, where for each pixel, maybe you didn't record what the number was. Maybe you recorded what the difference of that pixel was versus the pixel to its left. And so then suddenly the numbers would tend to get a lot smaller. So that's just an example. Or essentially, compression is something that comes up a lot. And so this is my kind of zoomed in, kind of simple example of how that might work. Now this compression is called lossless. Because I've changed the data around to take up less space, but I haven't given up any fidelity at all. If you run through my delta scheme here, the samples, they come back exactly right. Right? I haven't given up anything. I've just added complexity to take up less space. Just as an example, so PNG, I've talked about that as I think a little bit as an image format. So PNG is also lossless. It takes in a bunch of pixels. It rearranges them to take up less space, but the image is not corrupted in any way. It comes back perfect. So lossless formats, I think, are a little bit more rare. The more common approach to compression is what's called lossy compression. And so lossy compression is going to take in the data, and it's going to rearrange it so it takes up a lot less space. But it's not going to on playback, it's not going to reproduce the data exactly. It's just going to be sort of qualitatively very close. So you pretty much can't tell. So JPEG, that's the format where Lord knows we've been using that a lot. JPEG is actually lossy. And I'll demonstrate this in a little bit. So you can give it an image with the pixels just perfect, and it takes up a certain amount of space. You encode it as JPEG, and it will take up a lot less space, maybe 10x less space. But it'll make certain shortcuts about how the reds and the greens and blues are recorded. So when you look at it, it looks very good. But if you put it under a microscope, you could see where it had kind of fudged a little bit to save space. So I can do a simple example of a lossy compression, sticking with my audio sample example here, would be, what if, I think I have this, oh yeah, what if we just threw out every other number? We just said, well, whatever, we've got 44,000 of these a second. Let's just only record 22,000. And then on playback, they were going to have to know that. So we're going to record this number and this number and this number. And then on playback, what could playback do? Playback's going to have all these missing numbers, right? So it'll get this number and this number, and then playback is going to have to sort of fudge this middle number. What could playback do there? You could just guess, right? You could say, well, let's guess that it's halfway in between. We're going to just guess 12,003. Well, maybe in reality it was 12,002. That's probably going to sound pretty good, right? But this is a little bit lossy. We're fudging the data a little bit, right? So then the next one would be 12,010, 12,006. So again, maybe it would guess 12,008, even though in reality the sample was 12,007. Now this is a big savings, right? So this halves the space. My delta scheme also more or less halved the space, maybe even a little bit better. So you could pile these techniques on where your data was originally quite large. It could take up a lot less space. And when you play it back, so I'll do my JPEG example, it really does look very good. But if you got out the microscope and looked, you could see where certain little, fudge is the word I want to use, but there's probably a better term. Little adjustments have been made, so it takes up less space. OK, so the two, so any media data that you've played with, so JPEG for images, MP3 for sound, and all the video formats, make heavy, heavy use of lossy compression, especially video data. If you just had all the samples and you just recorded them in the raw, it's an enormous amount of data. Fortunately, the data, like I said, with the pixels and like the pixel right next to it, the pixel is said to have a lot of redundancy in it. That actually there are these patterns in the data that you can take advantage of to compress it quite a lot and have it still look very good. JPEG does this for images. MP3, which isn't that like the definition of being in college? No, I guess not anymore. I guess that's just being alive. MP3. Anyway, so MP3 is aggressively lossy. It starts with a lot of data, and it has all these tricks to throw out and cut corners a little bit to get it down to be pretty small. As I mentioned before, MP3 data works out to about 1 megabyte per minute, about 1 million bytes per minute to record pretty high quality audio. I should mention, MP3 was the result. That format was the result of a lot of research. That they had test subjects, and they would play sounds with different compression schemes and really home in on, for the human ear and brain, what are kind of fudges and omissions that can be heard and what are omissions that cannot be heard. And there was a lot of creativity and research went in to having MP3 work pretty well. And that was like, I don't know what, maybe 15 years ago or something. So in fact, then there have been advances since then, where the formats have gotten even better, where they take up less space than MP3, but also make their trade-offs even more cleverly, so they even sound better than MP3. Alrighty, so that is so lossy compression is just like part of life.